We started with the question of whether or not a robot can optimize space in a warehouse. In our initial brainstorming session, we considered all of the functions we wanted our robot to perform. It would have to be able to move independently around the warehouse, scan various packages as though they were supplied with a barcode, independently lift those packages, and distribute them to their appropriate destinations. We decided a robotic forklift would be the best tool for completing our task. The initial design process and construction took roughly 8 hours to complete. However, additional time was spent tweaking and adjusting our device once we began programming, including a redesign of the forklift apparatus. We used the LEGO Mindstorm's color sensors and built blue and red boxes they could detect. Once we determined the forklift was able to lift and carry the boxes, we programmed the various pathways it would have to take in order to transport the boxes to different locations within the warehouse. Initially, we wanted to have 6 different boxes. However, this number was unrealistic. We settled on 3 boxes for each run, and either box could be red or blue, and the robotic forklift would have to take every box to its corresponding destination. We realized our task could have substantial real-world applications. Not only does a robotic forklift reduce the required amount of human intervention, it can also be beneficial when transporting dangerous goods and potentially reduce the likelihood of inconsistencies in delivery. In a warehouse, a robot would grab a package, read its barcode, transmit that information to a centralized computer system, and store items in a designated department. Theoretically, a robotic forklift could be programmed to coordinate specific actions or use additional sensors to adjust its path if it detects irregularities during the pickup or transmission procedure. The concept map we built around this question illustrates the interrelationships between planar geometry, robotics, and design. We utilize planar geometry frequently during our programming session. In order to optimize space in a warehouse, we needed to be cognizant of the most efficient way to utilize it. Our process required knowledge of angles, area, and shapes to accomplish this. We used the integrated hardware and software of the LEGO Mindstorm's EV3 kit to complete our task. The software told the robot where to go and whether it should raise or lower the forklift arm when it got there. The design process of the robot was perhaps the most important part of the concept map, as it marries the 2 previous disciplines, math and technology, in order to ultimately carry out the task. Through design, trial and error, and our brainstorming, we were able to finish our project on time. Considering that STEM literacy might include some combination of 1. Awareness of the roles of science, technology, engineering, and mathematics in modern society, 2. Familiarity with at least some of the fundamental concepts from each area, and 3. A basic level of application fluency, we believe our project demonstrates multiple connections to the STEM education curriculum. While Bybee's case for STEM education argues that work-based learning and career and technical education programs are the pathways to prosperity that schools, especially high schools, should implement, Apparently, educational products such as LEGO Mindstorms provide elementary students with an engaging but challenging invitation into the STEM disciplines. In examining the elementary science curriculum provided by Alberta Education, it is obvious how this type of project would engage students in a process of inquiry and problem solving in which they develop both knowledge and skills. Based on our group's experience, designing, engineering, and building a robot is an excellent way for students to become personally involved in their learning. When they have a vested interest in their work, they will be more engaged for a longer period of time. This LEGO Mindstorms project is an excellent illustration of both inquiry-based learning and problem-solving through technology. By identifying a strong central question, our project stayed on track, and we developed a product with a potentially viable, practical application. However, the inquiry learning process and scientific investigation in general is fraught with the potential for frustration. It is important for teachers to be able to empathize with their students as they work through this type of project. We also found strong links between our specific task of designing and building a robotic forklift and the mathematics curriculum, specifically with the mention of building with quantities, searching for patterns, sorting objects, ordering objects, creating designs, and building with blocks. Consequently, completing this assignment has been pedagogically informative for our group and permitted a deeper understanding of STEM integration.